Hey, it's Miss Bruno, your math teacher. We used to see each other on the daily. Um, we're going to talk about this 3-9. I kind of hate this. I like teaching it, but I don't think you're going to get a lot out of it the way it is. Okay, so we're going to talk about this idea of end behavior, and end behavior is super important. And basically, it's what happens. Like, where is the graph going as X gets really, really big or X gets really, really small? And what you're going to find is that a lot of these equations are going to the same location, but they are going at a different pace. So, like, the idea of infinity, yeah, you can never get there. But if you could get there, some of these guys would get there quicker than others. Like, they're on their way there quicker. So it's talking about levels of infinity, which is a really abstract idea. And it's talking about rates of change. Okay. So these are the graphs we're going to be comparing. And they're going to have you compare them on this little grapher here, but it's kind of confusing unless I was there to lead you through it. So I think you'd be like, what the what? So we're just going to talk. So we're going to talk about these guys when x equals 0. When x equals 0, we're talking y-intercepts here. X equals 0 or y-intercepts. Which one of these is the biggest? We're going to do the biggest. And which one of these will be the smallest little baby? Okay, so these are the y-intercepts. Well, so what's the y-intercept of this? This is exponential growth, guys. Exponential growth always starts at 0, 1. It's increasing so fast, double, double, double. Y-intercept here is 1. What's the y-intercept of this guy? It would just be the constant when you plug in 0. So this is 1. 1 to the 5th is 1. I'm a liar? It's not. I don't know why I said that. The y-intercept plugging in 0, not 1, is 0. The y-intercept of this guy is -4. Y-intercept of this is 30. This is exponential decay. Plug in 0, you get 1 on this guy. 1/2 to the 0 is 1. This one's -20. This one is -1. And 0 to the 6 is 0. Okay. So which one of these was the biggest? Well, that was this guy. K of x was the biggest. That was the line of x plus 30. Then we had, what do we have? Big numbers, a whole bunch of ones, whole bunch of oneers. So we had f of x, which is 2 to the x. These are all tied. I'm going to put that decay one there. N of x, which is 1/2 to the x. And then you had this polynomial with y-intercept of 1. X to the 5th minus 4x squared plus 1. Those are all tied there. Pretty big. Not so big, but okay, we got those. Then we had 2 at 0 that were tied. That is x to the 5th and x to the 6th. Then I had a -1er, x to the 4th minus 1. Then a -4, x cubed plus x squared minus 4. And then we had x squared minus 20. Okay, so for a value of x equals 0, we have a defined list of the smallest to the biggest by the y-intercepts. You could see them by the graph. I put them in order on my little graph sheet that I attached to this. Okay, now this next idea. What if x is like really big? Really big, a very large number, so large that we say it's going towards infinity. Put them in order from smallest to biggest. Well, first of all, you're going to have a little bit of a problem here. So let's say that you say 1,000,000 is a really big number. What's 1,000,000 to the 5th? Well, that's pretty big. That is a pretty big number. I'm not going to lie. If I take that to the 5th, I don't want to write it down. And what about a million to the 6? Also super big. Which one is bigger, a million to the 5th or a million to the 6th? Well, a million to the 6th is bigger. Do I even need to know exactly what it is to put it in order? No. Sometimes you could say maybe 10 is just really big if you want to. 10 is not really big at all, actually. But if it helps you just put them in order, that's what we're talking about here. Because guess what? How about 2 to a million? Woo doggies. 2 to a million, you can type that bad boy in your calculator and it's going to say, hey, stupid, I can't do that. That's really super big overload or something. We don't do stuff like that. Is 2 to the million bigger than a million to the 6? Yeah, the answer is yes. Exponential growth grows so fast, so super fast. It's kind of scary, especially as you get to those exceptionally large numbers. Okay, so we are going to put these in order from greatest to smallest. I'm going to go this way this time. How about I put smallest over here, biggest over here, and this is as x goes to super bigness to infinity. So I just said 2 to the x, woo dogs, so big. That's got to be the biggest. Because even if you get to the biggest number you think of, double it again. It's going to be so, so big. My cursor, where did you go, cursor? Are you joking? Is this a joke right now? There it is. Okay. So we have that guy. Now, what else is really big? Okay, well, I have x to the 6 is really big. A million to the 6 has to be bigger than a million to the 4th. A half, that's decay. That guy's getting small. That's getting small. Okay, and then I have, that has to be the next biggest one, right? G of x is x to the 6th. If you take a million to the 6th power, that's pretty stinking big. So now I have these two guys. Which one of these is going to be bigger? A million to the 5th has to be bigger than a million to the 5th and then take away some stuff, right? So now I have x to the 5th, and I'm just going to write h of x here because I don't want to write that all out. But when I take some stuff away, it's not as big. Okay, so these are the ones I have left. How about this? A million to the 3rd plus a million squared. That's going to be pretty big. But how about a million to the 4th? Which one of these would be bigger? And the answer is always going to be this higher degree. A million to the 4th is going to be bigger than any cubic. Because as you type in exceptionally big numbers, if you don't do a million, think of 20 million or 100 million or a billion. A billion to the 4th has got to be bigger than a billion to the 3rd plus a billion squared. And that's hard to think about, but it is true. And then you have p of x here. That's that x cubed guy. Then you're looking at x squared. Then the line, the x plus 30. And the smallest of these guys, as you plug in really big numbers, is this exponential decay. And why is that? Well, think about it. As I plug in really big numbers, this guy is on its way to the asymptote of 0. This guy is getting smaller and smaller until it almost gets to 0, but not quite. So all of these guys are heading to infinity. If you plug in super big numbers, they're going to infinity. It's going up forever. All these graphs are going up forever except this guy. But this guy is going to be leading the pack. He's going to be going up the fastest as you're considering these exceptionally large numbers. Okay? Now, when you do negative infinity, the idea is similar. So if you plug in exceptionally small little friend numbers, okay, so now we're taking x to negative infinity. Really small babies. If you plug in a negative number here, think about it. Little number over here, we're going to 0. So this guy is heading towards 0. X to the 5th from outer space, guys, is a snake baby graph. It might not be right there, but from outer space, it looks like a snake baby. And this guy is going down. So this negative number will be taken to the 5th power, which is really super small. This is a super small. Same thing with this guy, which would be a super small. X to the 3rd, another snake baby. Super small as you are going for real big numbers. This one is also a small one. 1/2 to the X, that's your decay. What happens when you plug in really small numbers here? This guy is going up. This guy is going up, up. This is going to super big. Super with a B. That's how I spelled that. Super big. This guy is a parabola. When you plug in a negative number and square it, this guy is getting big as well. This is an up and up. All of these are getting big. Okay. So we're going to put this in order from smallest here, and we'll put the biggest here. As you're going to negative infinity, the left side of this graph. Okay, so let's look at these big ones first. Okay, so these are my choices for the bigs. Which one of these is going to be up the highest for those really small numbers? And it's always going to default to the exponential growth or decay. N of x in this case is going to be the biggest number because it would be like doubling when you plug in those negatives. Then if you plug in negative 1,000,000, which one is the biggest? It would be the biggest when you take it to the 6th power. That'll be q of x, then the 4th power, then the square. So all those even ones are big. And then we have this guy here at 0. So he will be in the middle. As you go to the left, this exponential growth guy will be in the middle because it's on its way to 0. And now we have all these odd degree polynomials that are going to get small. Now, which one will get the smallest the fastest? Well, if I plug in negative 1,000,000 to the 5th, that's really small. If I take negative 1,000,000 to the 5th, and then I subtract some more, h of x is going to be the smallest this time. Then r of x, those are the 5ths. Then I have my 3rd here, which is p of x, and then the line is kind of slow and steady, that constant rate of change. Okay, so all of these here, all the way here, these are all going to infinity. These guys are going to negative infinity. We have the f of x going to 0. These are just going faster than these. Those different levels of infinity. Okay, so this is these ideas of going to infinity, and we're going to take a break there, and then I'm going to do this chart is on the, I already posted it, but this is the next page that we're going to do, and this is an important page, so I'm going to stop the video there for those of you who already bailed ship on this bad boy.